Okay, this is the fourth tutorial, and this tutorial is going to introduce us to electric circuits, and I'm excited for this tutorial. Um, this tutorial is meant to be very hands-on. You're supposed to be playing with the batteries and the bulbs and having an experience here, and as you know, that's just not happening this semester. So we're just going to make the best of it. Okay, and I'll just try to be your avatar and uh, do the handling of the circuits, and hopefully we'll get something out of it. Let me just share my screen real quick. Um, so this is the tutorial. It's in your packet. It's one of the published tutorials. And it says that we're going to construct a model. And by model, we mean a uh, group of rules, uh, a recipe, if you will, that allows us to um, predict and explain the behavior of simple electric circuits. And the first activity we're going to do is each of you are going to get a battery and a light bulb and one single wire. And then you're supposed to find as many different ways as possible um, to make that bulb light up. And it turns out that you should be able to find four different ways to make that happen. And so let's talk about that. Now, one thing that I see very often is something that I call the Coleman method, where the wire is attached to one end of the battery, and then we hold the bulb uh, to the other end of the wire, expecting the bulb to light up. And the bulb doesn't, okay? But the thought is that if this were a Coleman lantern, I'd take the source of the energy, the gas, and then I'd provide a path to get it to uh, the part of the Coleman that glows, where it would be consumed. But that's not the way circuits work. And so that does not work. I'm going to just draw a real quick picture of that. And we know that I can't draw, but that's my best guess at what it would look like. Now, another way that students try when they're beginning is to take this wire and hook it from one side of the battery. Oops. Take this wire and hook it from one side of the battery to the other. Now, I and and I don't want to do that. And I don't want to do that because I've experienced it. Um, if I touch this side of the wire to this other end of the battery, very, very quickly that wire is going to get so hot that it's going to burn me very badly. And if I could hold that wire there um, long enough, if I were Superman, that wire would just start smoking, and then it would just, start to melt the casing right off of the wire, the plastic casing. So we're not going to do that, but I'll just draw a picture of it. Now, just so you know, uh, the bumpy side of a battery is the positive side, and the flat side is the negative side. And so what is often tried is the wire goes from here to here, and then the bulb will be placed like that. And that just doesn't work. Okay. So let's look at some things that do work. Um, One thing that works is to put one end of the wire on this side of the battery and then take the bulb and hold it so that the side of the bulb is, I'm not very coordinated, but you see what I'm trying to do here. I'm trying to hold the side of that bulb on the bump. And then I'm going to take the other end of the wire and touch it to the end. And sure enough, that bulb lights up. Okay. Now, this other way is going to be even harder for my uncoordinated hands. I'm going to hold the bumpy end of the bulb, uh, the bottom of the bulb to the end of the side of the battery, and then I'm going to touch the side of the bulb with the wire. And so if I draw those, it might make it clear what I was doing with my fat hands. So the first thing I did was I put that bulb on its side and I took the wire and connected it from this side of the battery to the bottom of the bulb. And then the second thing I did was I put the bottom of the bulb on the bump and took that wire and hooked it to the side. Now it says we should have found 4 different arrangements. And so we found 2, but I think it isn't a big stretch to say, well, if I turn the battery around and put the bulb on this side, it's going to light up. Okay. And likewise, I can get one where the bulb is on its side. And okay, so those are the 4 ways. Um, and they differ from the arrangements in which the bulb doesn't light, in that in these 4 cases, there are 2 special parts of the bulb that are involved with the circuit. And those 2 parts we call the terminals of the bulb. And the one terminal is this pointy end at the bottom. Where did my bulb go? There we go. It's this pointy end at the bottom. And then the other part that's special is the side. So we call these uh, terminals. And so in order for the bulb to light, one terminal of the bulb has to be connected to one side of the battery, and the other terminal of the bulb has to be connected to the other side of the battery. For example, if we look at this one here, the terminal at the bottom of the bulb is connected to the positive end of the battery, and the side of the bulb is connected through this wire to the negative side of the battery. Okay. Now, this activity here is a thought experiment. And that thought experiment is we're going to take a piece of nichrome wire, and nichrome wire is different from connecting wire. As I said just a moment ago, if I put connecting wire from one side of the battery to the other side of the battery, um, it gets hot really, really fast to the point of melting. It just so quickly. But nichrome wire has a higher resistance. And so when it's hooked to the battery, uh, we don't get that same result. It does, however, get warm, and we can infer that because we need um, this complete circuit, this route from the positive terminal of the battery to the negative terminal of the battery, in order for the wire to get warm, if I just hold it onto one terminal, nothing happens. But if I hook it to both sides, it starts to get warm. And if I infer that it's the flow, that something has to be flowing in there, and that it's that flow that's causing it to be warm, then I want to see where it's warmest. And what I find when I hold on to that is that it feels the same warm all the way around. I don't get any different temperature here than I do there than I do there. It's the same all the way around. Now, if it's the flow that's making this wire warm, what that tells me is that um, it's it's got the same flow everywhere. That whatever's flowing, I don't know, you might think it's electrons, I might think it's blueberry juice. Whatever's flowing doesn't get used up. Whatever I have flowing here is still flowing there, and it goes round and round and round. Okay? So whatever's happening at point one is also happening at point two and is also happening at point three. Okay, let's go to the second page here. Um, we want to uh, investigate conductors and insulators. Now, to do this, I'm going to um, I'm going to change the camera real quick. Okay, and what I'm going to do first is I'm going to put a bulb in a socket. Now, you'll see that this socket um, has a way to connect the two terminals of the bulb. Um, see, I should be left-handed. Yeah, okay. If I screw this into the socket, what I see is that this conductor here um, is connected to the side of the bulb, and this conductor here goes to the base of the bulb down at the bottom. Okay, and so I'm able to easily connect wires through these little attachments here to the two terminals of the bulb. Now, what I have here is a situation where I have a couple of batteries, and we say these batteries are in series with each other. They're just kind of helping each other out, pushing in the same direction. And what we're going to do is um, we've got a complete circuit here. Let me get some more real estate there. So we have this circuit that is incomplete. If I touch these two together, you see that the bulb lights because now I have a complete path from one side of the batteries to the other side of the batteries that includes that bulb. Now, if I if I put something metal in between these, um, the bulb lights up again. Okay. Anything I put that's metal or a conductor is going to make that bulb light up. On the other hand, if I put something like plastic or glass or um, a, some sort of uh, porcelain, the bulb does not light up. So here I've got a plastic ruler is what I've put in the circuit, and I get nothing. Okay, now there's a special case, and that's the case of graphite. If I take uh, a small piece of graphite and I put it between those wires, what I get is the bulb doesn't light up, or if I do get it to light up, it just barely, barely lights up, just a flicker. But if I have a bigger piece of graphite, I can get the bulb to light, but it doesn't light as brightly as it did before uh, when I had metal that was much brighter. And so what we find is that graphite is a conductor, but it's a poor conductor. It's kind of a in-between case, uh, just not your best conductor. Okay, so what is similar about most of the objects that let the bulb light? I'm going to go back to the other camera. What is similar is that metals, conductors, complete the circuit and light the bulb. Okay, now if we carefully examine a bulb, we find that there's two wires in there that support the filament, and I'm not sure there, that's probably the best you're going to see it. Um, anyway, it looks like this. Where this is a bead of glass that's holding these two wires apart, and this is the filament here that glows. Now, we want to take a good guess as to where those wires are attached. Um, down in here in the base where we can't see things. Well, what we notice is that on the side, we have a little bead um, of um, solder, and then down at the bottom we have a bead of solder, and that's where these wires are connected. One of them goes down to this terminal, and the other one goes over to the side where it's soldered on. And so when we put this into our little socket that holds the bulbs, one of the connectors connects here and one of the connectors connects there, so that current, the flow, can go up one of the wires through the filament, causing it to glow, and then out the other way. Okay. On the basis of the observations that we have made, we're going to make the following assumptions. And upon these two assumptions, we're going to build our entire model of electric circuits. First, a flow exists in a complete circuit from one terminal of the battery, one side of the battery, through the rest of the circuit, back to the other terminal of the battery, through the battery, and back around the circuit, just round and round and round. We're going to call this flow electric current. So I need this complete loop to get this flow. And the second assumption is that for identical bulbs, and by that we mean they were made at the same factory by the same worker on the same day, his name is Sven, bulb brightness can be used as an indicator of the amount of current through that bulb. The brighter the bulb, the greater the current. Well, if there's no current through the bulb and it's dark, and some current through the bulb makes it light up, it seems reasonable that even more current is going to make it even brighter. And I like to call this the more flow, more glow principle. Okay? Now, starting with these assumptions, we will develop a model that we can use to account for the behavior of simple circuits. The construction of a scientific model is a step-by-step process in which we specify only the minimum number of attributes that are needed to account for the phenomena under consideration. So we want our model to be as simple as possible. Well, let's start building our model. The first thing we're going to do is we are going to set up a two bulb circuit with identical bulbs. Whoops, sorry. We're going to set up a two bulb circuit with identical bulbs connected one after the other as shown. Bulbs connected in this way are said to be connected in series. So the first thing we're going to do is connect some bulbs in series. And we want to make some observations. We want to compare the brightness of the two bulbs with each other, and we want to pay attention only to large differences in brightness. We may notice minor differences if the two identical bulbs, in fact, are not quite identical, if that worker didn't quite do his job quite the same when he made each bulb. So let's quickly go over to our other camera, and we're going to set up that circuit. I've got a second bulb here, and I'm going to put that in series with the first bulb. Now, let me see if we can get everyone in the picture here. There we go. Now, what I am seeing is that the brightness of that bulb and the brightness of that bulb are pretty much the same. Pretty darn close to the exact same as each other. And I'm also noticing that that they each are dimmer than a single bulb. A single bulb all by its onesies is very, very bright, but the two bulbs in series are dim. Okay. Now, let's talk about what that tells us about circuits. So, is current used up in the first bulb, or is the current the same through both bulbs? Well, if we believe that more flow, more glow, we know that current is the same in both bulbs. And we know that because they're the same brightness. Now, that means that current isn't used up. If current were used up, then if current was going clockwise around here, then this top bulb would be brighter than the bottom bulb because it would get all of the current and the bottom bulb would just get what's left. Or if current was going the other way, then this bottom bulb would be brighter because it got all the current and the other one got what was left. But it didn't happen that way. They were the same. Do you think that switching the orders of the bulbs might make a difference? Uh, no. I'm not going to switch back to the camera to do that, but it doesn't. It just never does. Uh, on the basis of your observations alone, not from something you read in a book, can you tell the direction of the flow through the circuit? And the answer is no. Indeed, if I were to turn the battery around, everything would happen exactly the same as we observed. Now, compare the brightness of each of the bulbs in the two bulb series circuit with that of a bulb in a single bulb circuit. The two bulbs are dimmer. Now, let's use the assumptions we have made in developing our model for electric current to answer the following questions. How does the current through a bulb in a single bulb circuit compare with the current through the same bulb when it's connected in a series with a second bulb? I get greater current through the bulb in the single bulb circuit. What does your answer to question one imply about how the current through the battery in a single bulb circuit compares to the current through the battery in a two bulb series circuit? So if I draw those two circuits, remember this is our symbol for a battery. If I draw those two circuits, since this bulb was bright and more flow means more glow, I would say that there's a lot of current going around that circuit. And you remember we found with the nichrome wire that whatever flow I have here is the same as the flow here, is the same as the flow here, indeed is the same as the flow through the battery. Since these bulbs are dim and more flow means more glow, I must have a small amount of current going through this circuit, through this battery and through these bulbs. Okay. We may think of a bulb as presenting an obstacle or resistance to the current in the circuit. Thinking of the bulb in this way, Would adding more bulbs in series cause the total obstacle to the flow or the total resistance of the circuit to increase, decrease, or stay the same? Well, if the obstacle is making it harder for the current to flow, and we found that adding a bulb in series gives us less flow, that means we must be increasing the resistance by adding a bulb in series. Now, formulate a rule for predicting how the current through the battery would change, whether it would increase, decrease, or remain the same if the number of bulbs connected in series were increased or decreased. So, uh, if I increase the number of series bulbs, I'm going to write the current of the battery. We'll use capital I to represent current through the battery, goes down. And if I through the battery would increase. So for example, if I started with 2 bulbs in series, I would have very dim bulbs. But if I put 3 bulbs in series, I might have such a small current that the bulbs wouldn't be glowing that I could see much at all. Well, now we're going to go in a different direction. We're going to set up a 2 bulb circuit with identical bulbs so that their terminals are connected together as shown. Bulbs connected together in this way are connected in parallel with each other. Okay. Um, when the terminals of the bulbs are connected on both sides with wire, we say that they are in parallel. So let's set that up. Again, I'm going to move over here to the other camera. Where did my camera go? Huh. Oh, I selected the wrong one. My bad. Okay. Now, this time we're going to connect this bulb to both sides of the battery. And then we're going to connect this bulb to both sides of the battery. Now, let me get some of these things out of there. And what you see are that we have 2 bulbs that are equally bright. And indeed, if I unscrew one of the bulbs, I see that it doesn't significantly change the first bulb. Okay. Um, right now, they're both equally bright. And by going back to the single bulb circuit, it doesn't change the brightness of that first bulb. Okay. Now I hope you can see the circuit. There's the battery, and it goes through this bulb, and then it also goes through this bulb here. So it's kind of spaghetti there, but it is exactly as we have on the paper. Okay. The brightness, both bulbs are equally bright. And that means current through each bulb is the same by more flow, more glow. Describe the current in the entire circuit. Base your answer on your observations. In particular, how does the current through the battery seem to divide and recombine at the junctions of the two parallel branches? Well, if I say more flow, more glow, then these two bulbs had the same glow, so they had to have the same flow. I'm going to call that 5. Now we're going to figure out some units for that later, but for now it's just 5, whether you want to call it 5 quarts of blueberry juice per second, or whether you want to call it 5 amps, it's up to you. But if it's 5 in this bulb, it's 5 in that bulb, and that's just because they're the same brightness. But that current had to come from somewhere. And so when the current got to this junction here, 5 had to go this way and 5 had to go that way. And that must mean that we brought in 10 there, and the current through the battery is 10. So if we follow that around, we've got this 10, whatever we measure flow in, coming out of the battery. It gets to this junction. 5 goes this way and 5 goes that way. And we shouldn't expect more to go to the left or to the right because these are identical bulbs. We can't tell one from the other. And then those two currents, the 5 that go through this bulb and the 5 that go through that bulb, recombine right here at this junction to 10 and go back through the battery. Now, if I just had a single bulb, what we found was that the single bulb was just as bright. However bright these guys were, this one was exactly the same. And so that means it must have five whatevers. And now there's just a single path, so we know that the current through the battery is going to be just 5. So by adding this extra path with a bulb, we increase the current through the battery from 5 to 10. We doubled it. We doubled it. Now, is the brightness of each bulb in the two bulb parallel circuit greater than, less than, or equal to that of a bulb in a single bulb circuit? It's equal to. And how does the amount of current through a battery connected to a single bulb compare to the current through a battery connected to a two bulb parallel circuit? The current through single bulb circuit is half as much as through the two bulb parallel circuit. Formulate a rule for predicting how the current through the battery would change, whether it would increase, decrease, or remain the same if the number of bulbs connected in parallel were increased or decreased. Base your answer on observations of the behavior of the two bulb parallel circuit and the model for current. So, more bulbs in parallel, the current through the battery increases. Okay. And if I remove bulbs in parallel, the current through the battery would decrease. What can you infer about the total resistance of a circuit as the number of parallel branches is increased or decreased? Um, as we increase the number of parallel branches, the resistance of the circuit decreases. And we can go the other way as well. Does the amount of current through a battery seem to depend on the number of bulbs in the circuit and how they are connected? Yes. And think about this for a moment. Um, the current through a battery can't always be the same. If you've ever dealt with a battery in a car, you know that you can grab the terminals without being hurt. Um, the resistance in your body is great enough that you don't get any significant current flowing from one side of that battery to the other side of that battery. But if any of you have ever accidentally dropped a wrench across the terminals of a battery, you know that that's dramatic. I mean, you get so much current that you can actually weld that wrench right to the terminals of the battery and then cause an explosion. You never do that twice. You never do that twice. And so the greater the resistance um, in the circuit, the smaller the current through the battery. Okay, unscrew one of the bulbs in the two bulbs parallel circuit. We did that. Does this change significantly affect the current through the branch that contains the other bulb? No, we found that it just kept on glowing the same as it did. A characteristic of an ideal battery is that the branches connected directly across it are independent of each other. And that's the way your house is wired. You have a power source. It's not a 12-volt battery, but it's the same principle. And then you have what we call a high line and a low line. And you might have the bulb in your front room connected, and then you might have the bulb in your kitchen connected, and then you might have your uh, microwave connected, and then you might have your blender connected. Um, and turning on the blender doesn't turn off the lights or cause the lights to flicker in your front room if things are wired up correctly. Okay, we say that these are each of these branches is parallel across the battery. They each have they each have connections directly to both sides of the battery with nothing but wire. Okay, last page. Now, we're going to find that this model that we've put together um, allows us to make a lot of predictions, but not all of the predictions. It turns out that we're going to find some situations where we get a conundrum, if you will, um, where we just don't get a definitive answer. And that's because this model that we have developed is very much a qualitative model. It tells us when the current through the battery is going to increase and when it's going to decrease, but it doesn't say by how much. Now we can investigate that with this thought experiment. The circuit at the right contains three identical bulbs and an ideal battery. Assume that the resistance of the switch when closed is negligible, so it acts like a wire. Use the model we have developed to predict the relative brightness of the bulbs in the circuit when the switch is closed. Well, when the switch is closed, all of the current goes through bulb A, and then we have current splitting through bulbs B and C. So I get all of the current here, and I get half here and half here. Now, why do I get half through B and half through C? Well, when the current splits right here, it sees two paths back to the other side of the battery. It can either go through B or it can go through C. Well, again, these are identical bulbs. There's no reason for the current to choose B over C or C over B. So this will be half, and this will be half, and this will be all of it. Now, what's going to happen to the brightness of bulb A when we open the switch? Well, if adding a path increases the current through the battery, removing a path decreases the current through the battery. So when I open the switch, I remove the path through C. That increases the resistance of the circuit, and that decreases the current through the battery. So now we want to show that a simple application of the model for current that we have developed thus far is inadequate for determining how the brightness of bulb B changes when the switch is opened. I know that A gets dimmer when the switch is open. Oops, too many P's in there. But I don't know, I can't know with my models thus far what's going to happen to B. And let's think that through. When I go to, when I open the switch, now all the current that goes through A goes through B. Okay, so A will be equal to B. I'm going to draw that again. Nothing goes through C. So C is out. It's on an incomplete path. But B is now getting 100% of the current through the battery, whereas before it was only getting half of the current through the battery. But the current through the battery got smaller. but we don't know how much smaller. If the current through the battery just gets a little bit smaller, then B getting 100% of that instead of 50% is going to get brighter. But if the current through the battery gets a lot smaller, then B is going to get dimmer. Okay. I think of this as a pizza problem. If someone asks you, would you rather have um, half of a large pizza or all of a small pizza? What's the first question you're going to ask? Well, how big is that small pizza compared to the big pizza? Okay. If I don't know that, I don't know how to choose, given that I'm hungry. Um, so all I know is that the current through the battery gets smaller. I don't know how much smaller. But in this case, B gets all of the small pizza, whereas in this case, with the switch closed, B only got half of the large pizza. And so in this case, our model fails to make a prediction for the brightness of B. And so we're going to need something else. And that's what we're going to develop next week in the next tutorial is a second half of this model. So that's the end of this tutorial. I hope that it went well, and I wish you all a great evening. Let's, oops. Okay, stop the recording.